It's
Okay.
recording now.
Okay, thank you.
Of course. Okay, so the first problem is regarding the buoyancy. When an object is submerged in water, what kind of forces are experienced by it?
Yeah.
So there are a few things. If you're heavier than water, which means your density is greater than water, things will totally submerge.
Mm.
But if your density is less than water, you're more likely to float. So there are always three scenarios that can happen. Um, One is where you're totally submerged. Actually, let me just, that's better. Okay. One is you will be completely submerged in water without any force, and that is when
Mhm.
your density of the object is greater than density of water.
Yeah.
Um, Sometimes you will float, and notice with floating, a part of the object is above the surface, part of the object can be below the surface. Um, that is when the density of the object is less than that of water.
Mm.
If the density of the liquid and the object are equal,
Mm.
they will it will float, but like right below the surface. Like this is the condition when the object and liquid's density are equal. It's kind of floating,
Mm.
but none of it is above the surface. In this problem, this spherical ball, you can see the density of it compared to that of water.
Mm.
It's actually lower, but it is stationary and it's totally submerged in water, which means there is like maybe there's a hand that's kind of like pushing on it, keeping it completely submerged.
Mhm.
Um, or actually, it could be this anchor, right? Actually, yeah, it's this anchor. I didn't see
Mm.
that first. It's this anchor and it's keeping it in the water.
Mm.
Part one is explain in your own words without calculations why there must be tension in the rope, which is attached to the object and anchored to the bottom. There will be tension in the rope. Remember, tension is actually a pulling force,
Yeah.
right? There will be tension in the rope if something is pulling on it, which means this object is trying to go up. That is what will create the tension. If this object was trying to go further down, there will be no tension in the rope, right?
Mhm.
So we know that this object is trying to go up. We just have to use this concept and the comparable densities to just explain that.
Mhm.
So the explanation for that would be, since the densities are, so density of the spherical object is lower than that of water, it means that it would want to float, right? So there will be a buoyancy force. I think it's just called buoyant force. Which means have you do you swim like or have you
Yeah,
been
yeah.
in water? Yeah,
I do some, yes.
right? You feel lighter in water.
Yeah.
And it's almost as if the water is carrying some of your weight. That is the buoyant force. So any liquid exerts an upwards buoyant force on any object. That is what we call the buoyant force. This is what keeps the objects floating in water.
Mhm.
That's the technical term for it. So we'll say that there is a buoyant force acting upwards. When the density of the object is less, it means buoyant force actually overpowers the object's own weight because gravity is trying to pull it down, right? There's Fg trying to pull it down, but the buoyant force will act upwards. And in case of this, the Fg is actually less than the buoyant force. And because of that, if you do the net force, it will be Fb minus Fg, which means because they're not equal, Fb is higher. It means there will be some kind of acceleration produced because of this, whatever this difference is.
Mhm.
And this acceleration will be in the upwards direction. Why? Because buoyant force is acting upwards. And because of that, the spherical ball or the spherical object, it experiences an upward force. Experiences an upward force, and that force is what leads to tension, right?
Yeah.
Yeah, so that's part A. Part B is the object has a radius of 5 centimeters. Calculate the tension in the rope. Your solution must start with a free body diagram. Okay, so again, like we initially said, there's going to be Fg. Yes, any object will have, as long as you're on Earth, will experience gravity. We know that there is going to be a buoyant force. What else do we know? What other forces can there be? And what do we know about the state of the object? Is it moving or is it stationary?
It's stationary, so tension is gonna be there as well.
Yes. There's going to be tension because it's tied to a rope or string. So anytime there's a rope string involved, there's going to be tension. Okay, so there's a tension force. We just established that FB is greater than FG. Another thing, sorry, I didn't complete that thought, but because it's stationary, it means F net should be 0,
Okay.
right? That's the concept that you should be using in any of the things that are stationary. It means all the sum of forces that are acting on it are 0. That's the concept. Okay. And what that means is the buoyant force, the Fg, the tension, the sum of all of that on your sphere is going to be 0. Okay, so F net is made up of FB. It's arbitrary, but I'm considering the upwards direction to be positive direction. You can take the downwards direction to be positive. It would just switch the signs. It doesn't matter. And then I'm calling it FG, but it's literally just the weight of the ball itself. Okay. And so that is equal to 0. Now we're finding tension.
Yeah.
So we'll just rearrange for it. I'm just going to move tension to the other side. So FB minus FG is equal to T. Now all you have to do is figure out what the buoyant force is, what is FG, and put it equal to 0. Well, let me see if there are formulas so you don't have to. Fluid dynamics. Buoyant force formula should be
They
here.
do have it there, yeah.
Oh, they do?
Yeah,
Okay.
yeah. Somewhere there. It's...
Oh, this one.
Yeah. Yeah.
Great. So the buoyant force is the weight of the displaced liquid. This is very important. The most important part that you have to take care of in this formula is this volume. In this question, it's just going to be the volume of the sphere, but sometimes when the object is half floating and half in water, like something like this, let's say half of it is just in water, the volume only talks about the displaced fluid's volume. So you would have to take just half of that. That's something, for this question, all of it is in water, so we'll just take volume of everything, but just to keep in mind for any other questions. Okay, so it's density of the fluid, volume of the displaced fluid, and G. So that's just going to be, density of water times the volume of the sphere times gravity. Okay. Another thing, we need Fg. Now, force of gravity is usually mg, but we don't know the mass of the sphere, do we? We don't. So But we do know, I'm going to call it object just to be consistent with the DO. But I don't know the mass, but I do know that the mass is basically, density is mass over volume, like this
Yeah.
formula, right? So I
Mm.
can just use the density and volume of the object. So density of the object and volume of the object to replace m. And they,
Uh-huh.
they gave me the density and the volume, right? I mean,
Yeah.
they gave us radius, so we can easily calculate that. So it'll
Mm.
be density of the object. Sorry, the symbol for density is
Yes.
rho.
Mm.
Sometimes you can use d, but rho is more
Mm.
technical.
Yeah.
Okay. And you have all the values now. You can
Mm-hmm.
just put everything in, and that will be equal to tension.
Okay. Yeah.
Right? Good. Can we move
Yep.
on to the next?
Yes.
Okay, perfect. Okay, this one is a tube, and we have water flowing in. Just to just a logical explanation, the more the area, the lower the velocity. So it says V1 and then there's V2 here, right?
Yes.
So remember that the narrower the pipe gets, the higher its speed.
Resistance. Yeah.
Okay, good. And yes, higher the resistance as well. Okay, so this we have a horizontal tube consisting of two sections. The gauge pressure, what is the gauge pressure? Is absolute minus atmospheric, right?
Mm-hmm.
Uh, it basically means that you're ignoring atmospheric pressure. Um, yeah, I think gauge is absolute minus atmospheric. At position one, so we know the pressure at position one, 850 Pascal. Assume water has a density of this. We have a viscosity of water given to us as well. We have radius at both positions. And P2 is P atmosphere, which means if you're considering gauge, you can just say the P at the position 2 is just 0. Do you know that concept that the relationship between gauge pressure and atmospheric pressure?
No, I don't think so.
Okay, I'll see in the solutions what your teacher has done. But
Mm.
apparently, so there's atmospheric pressure and then there's gauge pressure, okay?
Yeah.
So let's say you're standing here and obviously you're on Earth, you experience the atmospheric pressure of the atmosphere over us, right?
Mm.
Um, when we consider gauge pressure, we just say gauge pressure is 0, which means we're like making like a baseline. Um, and any pressure that you experience after is going to be just the pressure of the thing that you're experiencing. For example, let me just make it more clear. Let's say you have a glass of water, okay? And there is this object here. Right now, this object will experience the pressure of this water, whatever much water there is, this red sections of water is going to put pressure on it. But then
Mm.
there's also this whole atmosphere that's putting pressure on it as well, right?
Mm.
When we talk about gauge pressure, we just ignore the atmospheric pressure altogether, um, just because it's like everything on Earth is going to experience atmospheric pressure anyway. So
Mhm.
just eliminate that, makes our calculation easier. It's kind of like setting a baseline, right?
Mhm.
So considering this, you would be experiencing a gauge pressure of 0 because we're ignoring the atmospheric pressure.
Yeah.
Um, this distinction is important. You either convert gauge pressure into atmospheric pressure, like add atmospheric pressure to this, or you make this into gauge pressure, which is easier
Mhm.
because your P atmosphere is just 0 for gauge. So this will be easier to do. But if you have questions like these, you have to remember that if one pressure is atmosphere and one pressure is gauge, you can't just add or subtract them. You have to convert them both into the same
Okay.
notation. Okay. Um, but I think we'll won't be using pressure at least in the first part. First
Mhm.
part is just calculating the flow rate, volume
Mhm.
flow rate. Um, Poiseuille's law. You should have equations for all of these in your
Yeah,
formula
yeah.
sheet, right? Okay, perfect.
Let's see if I
Uh,
have. It's up,
we
up, up, up.
is this one?
Yeah, yeah. No, no, no. Oh, yeah, I think that's the one. Yeah, that's the first one. Yes.
Yep.
It's
Okay,
that one,
perfect.
and then there's another one, like the actual law,
The
I think.
actual law. Okay.
Yeah.
Alrighty. Let's do the calculation for the volumetric flow rate, which is going to be actually pretty straightforward. You just have to input all the values in. Pi r1 to the power of 4.
Okay, so
You're given
which formula is this exactly?
which formula is this?
This
The
is this one's the law, like the formula for the law. Oh, okay, yeah.
uh I think so because you are calculating the flow rate taking into consideration the resistance.
Okay, yeah.
This is viscosity. Actually, I think you have a different symbol for viscosity. I'm gonna go back and check. What was this? N? Okay, yeah, this symbol.
Yeah.
Sometimes you use mu, but never mind.
Mm.
Okay, it's this. So usually what you would do to calculate the flow rate is just, multiply the area um, with the velocity,
Mhm.
area, length, and, velocities. That would give you the flow rate, but because there is resistance because the fluid is viscous, you'll be using this law. You're given all the parameters, so all you have to do is just plug in the numbers.
Yeah.
And it says the entire tube, so there are two sections. You can do it for the first section and then you can do it for the second section as well. So you can do both. The viscosity stays the same, but the length and the radius will change as per the every just solve with the given parameters. Yes, that
Mhm.
should be good. And they have one number, which I believe is because they probably uh, they added the total resistances and then did a
Mhm.
combined flow. So R1 and R2 is going to give you the resistance in the first one and the second one, and then you can find the total. Yeah, you can find the total resistance in the entire tube, just adding them both up. And after you can find uh, the volume. Let's do volume, volumetric flow rate, which means the amount of volume over time. Any flow rate, be it linear or volumetric or mass, it's always divided by time. So it's delta V over delta T or delta M over delta T. A flow rate formula is always, so this is what we're looking for. We have to look for a formula that connects volume and the resistances. So let's see, this is charge, this is, we can use this formula would work, right?
Mhm.
We added the resistances because they were in series, right? Sometimes the pipe just goes like um, this, like parallel. And in those cases, you will use this formula to calculate the total resistance.
Okay.
It's
Yeah.
it's very much like how we did it in, I don't know if you remember electricity when you would just divide into parallel
Yeah. Yeah.
resistances, right?
Yes.
Same.
Yeah. Yeah. Okay.
Yeah. Um, so this is the formula that has delta V over delta T. It has R, we just calculated R, and then it has the change in pressure. So what we're going to do is um, we're going to calculate change in pressure. We already have R, and then we'll be able to calculate the volumetric flow rate. In most of the instances in these questions, you will be able to um, like navigate most of the questions just by looking at the formula sheet and then, how things are
Mhm.
connecting different things.
Yeah.
So delta P is the change in pressure. We supposed that this was just zero and this is 850. So your change in pressure is just going to be 850 minus zero, right? Um, let's just divide by R on both sides because, this is what we want to find.
Mm.
This is delta V over delta T. So delta P is 850
Mm.
pascals. R is whatever value you will calculate here. That'll go here.
Okay. Yeah.
And then you will have your volumetric flow rate.
Okay.
Um, I think the units should be fine because this is
Mm.
SI unit and the length is in meters, the radius is in meters, so everything should be SI units.
Mm.
So the volumetric flow rate should be in meter cube per second,
Yeah.
I believe. That should be
Mm.
it.
Mm.
But just double check your units. Just make sure everything is in SI units before.
Yeah. Okay.
Good. Um, use equation of continuity and the result from part A to calculate V2 of the water exiting the tube. Equation of continuity is the A of the A1 V1 equals A2 V2 equals the total flow rate, right? It should be
Yeah.
somewhere here. Let me just
Yeah.
see.
Yeah.
You remember the equation?
Yes.
Okay, good. Then I can just proceed without looking at it. Um, okay. So equation of continuity is your total volumetric flow rate,
Yeah.
right?
Right. Yes.
Is A1 V1 equals A2 V2. And you can use any part of this. It's like sine law. You have three different parts, so you can use this or this as per your convenience. We don't know the velocity in the first section, right?
Yeah.
Yeah, they don't give us anything. So it will be better to use this and this
Okay.
because we already have the volumetric flow rate from here that
Yeah.
you will just input in here, right? So you'll
Okay.
just put that number here, and then area 2 is just going to be, the the area of the tube, which is going to be pi over 4 d squared. Or r, never mind. You could just do pi r squared because
Okay.
you have the radius, not diameter.
Okay, there's one thing in the B part, like okay, so it was like
Yeah.
delta V by delta T, and then it is equal to V to A2. And then
Yes.
there's like an arrow, and then it's like V2 is equal to delta V by delta
Yeah.
T by A2. I don't
Yeah.
get that why did we add delta V by delta T in the part above? Like V2 is equal to delta V by delta T by A2, sorry.
Oh, they're just rearranging it. So what they're doing is like, A2 V2 is equal to the volumetric flow rate.
Yeah.
So to find V2, what do? We will just divide by A2 on both sides, right?
Yeah.
So they're just doing delta V by delta T all over A2. That's
Oh,
just
okay.
rearrangement. Yeah.
Okay.
If you don't like rearranging, you can just input the numbers and then just solve from there. Like
Okay.
You can calculate area separately. This number
Mm.
you will already know, and you can just divide them if that's simpler for you.
Okay.
Okay, so this number is going to be this yellow number, and A2 you can calculate because A2 will just be pi and then R2 squared.
Yeah, so if we divide A2 on both the sides,
Yep.
so like they just input the value on the right side, right? The A2. What about the A2 on the
Yeah,
left?
A2 on the left.
Like you divided both the A2s, right? On the
Yeah,
other
so this
side.
cancels.
Oh, okay, okay, yeah, yeah, that makes sense. Yes.
Yeah,
Okay,
that, yeah, cancels.
okay.
Right? So let me just highlight this in a different color. This blue value will go here, and then you'll just divide
Mm,
both the answers.
okay.
Okay, and your velocity should be in meters per second because
Mm,
we're using all. Okay, good. I'm gonna have to add another page here. We're doing part C now.
yeah.
Okay, Bernoulli's equation.
Yeah, I had a hard time doing part C. So I just couldn't I couldn't understand so like
Okay,
some of the steps. Yeah.
so basically just a little bit of context on Bernoulli's equation. It's it's basically just the law of conservation of energy.
Mm-hmm.
So what Bernoulli says is total energy is always conserved, right? So if you have this tube and it's doing something like this, the total energy in the fluid at this point and total energy in the fluid at this point should be equal. So
Yes.
total energy at point one should be equal to total energy at point two. And there are a lot of things that are going on, right? Like there's pressure, there's speed, the liquid has some so if it's at some height, like sometimes the tubes are like this. So one thing is at a lower height, the other is at a higher height. So there like and because fluid is moving, they have kinetic energy, they have potential energy. There's
Mm,
obviously the pressure of the fluid because it's coming at some speed, right? Pressure
yes.
energy. So same thing here. So what Bernoulli's takes into account is the kinetic energy, the potential energy, and the pressure at the first point and
Mm,
puts it equal to the second point because, total energy of everything is
mm,
always conserved.
uh-huh.
And that is basically what the equation is. Just a little bit of background to understanding because
Okay.
it'll make more sense. So
Mm.
if you look at um, where is his equation?
Yeah, it's
Here,
there.
this one.
Yeah.
Yeah.
Yep.
So this means it's always conserved, it's the law of
Yeah.
conservation of energy. Energy of the universe is always the same. It never changes. It
Mm-hmm.
means the energy at point one, so pressure at point one, plus density of the liquid at point one, speed at point one, density of the liquid at point one. It's the same liquid, so we don't really need to write this because the density of the liquid won't change.
Mm-hmm.
Gravity won't change, but just the height might, right? If you have difference in the heights.
Mm-hmm.
It should be equal to the pressure at point two, the kinetic energy at point two, and the potential energy at point two as well. This is
Okay.
where the equations are coming from. Okay.
Mm-hmm. Yeah.
And the pressure at both points. This is 850. This was just zero. Maybe I should
Mm.
hold on. Let me just do it where the question is. I'm just gonna cut it and paste it here. Okay. What some teachers do is they just bring the P2 to this side. They're like P1 minus P2 is delta P. You can do that, but you can
Mm.
also just simply put the values in, right? Like
Mm.
we know P2 is just zero. I'll just put this as zero. I know
Mm.
P1 is 850 pascals,
Yeah.
right? We just calculated V2. Um, I did not calculate V1 though, and we don't have. Oh no, they're asking us to calculate V2 again. If the water is assumed to be an ideal fluid. Oh, maybe they just want the answers for V2 by different
Yeah.
approaches, like
Yes.
continuity and okay, okay, okay. So we're still finding V2. Gotcha.
Mm-hmm.
Um, so finding V2 again. Okay. Um, what else do we know? We know that if you look at them, they're practically on the ground, like this point and this point are on the exact same height,
Mm-hmm.
right? Which means there's no height difference, which means both of these things can be zero.
Mm-hmm.
If it was something like this, I will assume this height, let's say, to be zero, and then this is, let's say, was 2 meters. So then you will,
Mm-hmm.
for the other one, you'll just put y as 2 and you'll do the whole calculation. But when something is horizontal, it's just gone. And that will really simplify our equation. It will look something like 850 pascals or delta P. Some people could call it delta P as well. And then let me just move my, uh, you can just move your either delta P to the other side, or you could move um, this to this side, this to that side. It's up to you.
Mm-hmm.
I'm going to move it to the other side, like this one. I'm going to move to the other side because the
Okay.
unknown is V2, right? So,
Yeah.
okay, so we'll have 850 pascals equals, you can take the half P common because this is common in both, so
Mm-hmm.
you can just take it, factor it out, and you'll have V2 squared minus V1 squared, right? Does that make
Mm.
sense? Okay.
Yeah.
We know the density of the fluid. I think it was given to us. Yes, it's just water, so 1,000 kilograms per meter cube.
Mm-hmm.
The the problem is we don't know both V1 and V2.
Yeah.
So I gotta at least find one of them, or maybe try to substitute.
Mm.
And so here you will encounter a problem. So the problem here is two unknowns, V1 and V2. Okay, so
So
what do we do?
the thing is, we did calculate the speed in the B, like we did calculate the speed of V2 in the B bit, right?
Yes, but we can't, they're literally asking us to calculate it again here, which means we can't use the results from part B. It says your answer should be larger than what you got in part B, so you're not, because you're not considering the resistance to
Resistance to
flow.
flow. Yeah, okay, that makes sense. Yeah.
So we can't use that. So when there are two unknowns and just one equation, two
Mhm.
possibilities, okay?
Okay.
One possibility is you should be able to make another equation. Um, in this case, not possible because Bernoulli's equation is just this. We can't make
Mm.
any other equations.
Mhm.
Um, the other thing is you try to express one variable in the form of the other. Like you know how we
Mhm.
used to do the rectangle questions, it was like the length is two times the width. What is the area? You know, let's say
Mm.
something like that. So you would have width as W, but to replace L, you would just do because, the length was two times W anyway. So you would have just
Mhm.
one variable.
Mm.
So similar to that, um, we have to find some kind of a relationship between V1 and V2. We know
Mhm.
they're in the pipe. Okay. There definitely is a relationship between them, and the
Yeah.
relationship is the continuity equation,
Yeah.
right? Like the area of one times velocity of the one section
Mm.
here, should it be exactly equal to the area times velocity of the second section?
Yeah.
So what I'm going to do is I'm going to try and find V1 in terms of V2. So
Okay.
just by dividing by A1 on both sides, you'll get
Mhm.
this.
Okay.
You know the area of 2 because you know the radius. So it'll just be pi r2 squared times V2 over area of the first one is just pi r1 squared, right?
Yeah.
Okay. And then you can just cancel out your pi's. So when you write this equation, you'll have half rho. You'll have v2 squared, that's fine. But for v1, you can write it as, no, the pi's are canceled now. So you can just write it as r2 squared v2 over r1 squared. And one common mistake that students make is they forget to write this squared because the r has a squared already, right? So they usually forget the other squared, and this is where they might get the answer wrong. I used to make that mistake, so I remember, but that's all. And
It's just
yes,
that they did it a bit differently in like the solution paper, so I'm sort of confused. Like
um,
I don't
I
get.
think it's just rearranging. So let's do it. Let me just rearrange so it looks similar. So first of all, what you can do is just move the 2 to the other side with pressure. So it'll
Okay.
just be 2 times 850, right?
Mm,
And then you'll have rho. If you simplify this, you have v2 squared minus r2 to the power of 4, because, 2 squared,
mhm,
and then v2 squared over r1 to the power of 4 as well. Now you can see that v2 squared is common in both.
yeah,
So you can just factor that out. So you'll have 1 minus r2 to the power of 4 and r1 to the power of 4. And then um, you can move, obviously, your goal is to find v2, right? So you got to
mm,
move this term and this term to the other side. So one way to do that is I keep writing 850. They probably wrote delta p if
yeah,
that's right.
yeah,
And then you can divide by rho and this term on both sides. That is equal to v2 squared. And then to find just v, you can just square root the whole thing, right?
yeah,
So they probably have something like this. And then all you have to do is just input the numbers.
yeah. Okay. Okay, I think
Okay,
that's
so
how. Yeah, yeah.
all
That's
right.
okay.
Okay, good.
Yeah,
Okay, let's move on to the next.
yeah.
This one, we have a 10 kilogram mass attached to spring. By the way, just a little context about spring. Spring kind of does like a periodic back and forth motion, right? Like,
Mm,
and anything that does a periodic motion can be expressed in terms of a sine or cosine function. So that is something to note in this case. Much like the motion of a clock or like Ferris wheel, anything that is periodic, even waves in the ocean, like if they do something like that, you can express anything that's periodic in the form of a sine function. Okay, but let's read this. The spring right now is at an equilibrium position. It has a mass of 10 grams. It's on a frictionless surface. There's no friction, and it has a spring constant. Spring constant, basically, it's just a term that describes how rigid or flexible the spring is. Like the higher your spring constant, the more force you will have to apply to compress it. Like it'll be very rigid to any kind of change, right?
mhm,
So it's different for different springs. It just tells you what kind of spring it is. Um, Equilibrium position is kind of like when no force is being applied. This is where the spring rests. So right now, spring is not doing anything. It is at rest. It's stable. If you so right now it's like this. What you do is you pull it to the right. So it's at its resting position. You pull it 0.25 meters to the right. So like you kind of like just stretch the spring. So the spring right now is probably doing something like, oops, right? Something like that has happened. So now it's in a stretched phase. Now the spring is working. Um, so you stretch it. at a distance of 0.25 meters. And then from this position, while it's resting means you're just holding it there, so velocity is 0, you just release it. And then you release it at t equals 0. So t equals 0 means this is just the start of the time. Write down a mathematical expression for the position which describes the resulting motion. Remember, just think logically. What is your spring going to do when you leave it, right? It's going to like go back and forth, and then slowly come like it's going to do a back and forth motion, correct?
Yeah.
Okay. So, which means it's going to do a periodic motion. Anything that does a periodic motion, so spring will undergo a periodic motion. Okay. And for periodic motion, we use the trig functions. Sign is convenient. So usually the position function is kind of like this, okay? The position function can be described by, have you done trigonometric functions? Like, do you remember like doing this?
Yeah, a bit.
Something like that?
No, not this one. I just know sine, cos, and like the basics, basically.
Okay. So this is a sine function. All these
Mhm.
variables are just how, like, just transformations of it. So the
Mhm.
basic function is just sine x, right? But we can
Yeah.
modify it to suit our needs. So what we do is
Mhm.
we add amplitude. Amplitude is like the highest stretch you basically make it however much you stretch it, like the maximum that it can stretch or compress. That is A.
Mhm.
And then you put sine, and then you have um, omega t, which is t is basically like x. In this
Mhm.
case, the variable is t. We're measuring it against t. And then sometimes there's a phase shift.
Yeah.
By the way, the trig functions can be sine, can be cosine, depends.
Yeah, they used cos here. Yeah.
Okay. Cos, I think they used it because the cos graph goes like this, right? Like it
Mhm.
starts at a max position. Sine
Yeah.
graph starts at equilibrium position, right?
Mhm.
So because you're starting here, which is kind of like your max position,
Yeah.
corresponds to this. I think that's why they used cos. We can
Cos.
you just have to replace sine with cos. That's all you have to do. Okay, so that's A and then cos. Okay. What omega represents is the angular velocity or speed.
Yeah.
But anyway, um, this is going to be the skeleton of the equation that we're using. They probably want us to assume x equals 0 corresponds to the resting position, which means when t is equal to 0, when t is equal to 0, no, sorry, this is the resting position, the equilibrium position. They're just referring to this. Oh, right before pulling to the right is that. Okay.
Okay.
But when t is equal to 0, we know what x is. When t is equal to 0, what is this x?
Oh, yeah. 0.25.
Right? We
Yeah.
moved it,
Yeah.
so x should be 0.25. So what I'm going to do is I'm going to input these values into the equation and see what we get. Okay. Uh, if you input t as 0 into this function,
Mhm.
um, actually you don't even have to input t as 0 into this function. You know A is the maximum amplitude.
Yeah.
We know A is like the maximum stretch or compression that you can apply to the spring, and it is 0.25.
Mhm.
So you know that A is going to be 0.25 because that is the max you can
Mhm.
pull.
Okay.
Okay. And then the other thing is if you know that A is 0.25 and T is 0 and such, you can find the value of phi from there
So
because, yeah,
x is sorry so x is 0.25 and a is 0.25 as well.
yes, because A is
Amplitude,
the
got it.
maximum displacement, you can call
Okay.
it, right?
Mm-hmm.
So x
Yeah.
will vary. Like here, x will be different, x will be different. But the value of x at the maximum position is what A is.
Yes, got it.
Okay, good. Um, and what else we need to do here is we need to find the value of A and omega and this phi. Like we need to figure them
Mhm.
all out. We know A because we know the maximum displacement.
Yeah.
Um, we'll now try to find phi, and we will use these parameters. So we know that when t is equal to 0, x is 0.25. Um, we now know a is also 0.25, right? And the equation becomes something like this. Okay?
Yeah.
Um, because I'm finding phi, the first thing I'm going to do is just divide by 0.25 on both sides. Cancels, cancel. So you have 1 equals um, cos negative phi.
Mhm.
Okay? Cos, if you look at the shape of it,
Yeah.
is actually what we call an even function. It means it's symmetrical around both, which means no matter if I ask for positive 90 or negative 90 or like positive 180 or negative 180, like the values are going to be exactly the same. That's what an even function means. It means if you have a negative phi, that's your value is going to be exactly equal to if it was like a positive phi.
Okay. Yeah.
Okay. And so, which means 1 is equal to cos phi. And you can tell at what position of phi do you get the answer of 1. By the way, this is 1, and this is negative 1, and this is 0. So you get 1 when the angle is equal to 0.
Okay.
Okay, it is complete. You could do it in your calculator. Honestly, you can just do cos inverse of 1 and you'll get 0.
Mm-hmm.
Definitely. Or you can just study the graph. It's like that. 1, 0, negative 1. For sine, it's the opposite though.
Yeah.
For sine, at 0, at 0 the value is 0. Sine goes to 1 at 90 degrees. Okay,
Mm-hmm. Okay. Yeah. Yeah.
so just something to keep in mind.
Mm.
Okay, which means phi is just 0. So we found A. We found that phi is just 0, so that means it won't even appear in the equation when we write it. The
Mm-hmm.
only other thing that we're left to find is omega. So first we find A, next we find phi. Now we can find omega. Omega has a very simple formula. It's just the square root of k over m. It's
Mm.
probably in your formula sheet. I'll highlight that. You can go to springs. Mm, work energy. No, not here. Rings aren't here. Probably waves.
Yeah.
Yeah, this is more complicated version of the same thing we just did.
Yeah.
But I
I don't know. It's supposed to be there, but I don't see it. Uh.
yeah, it's maybe
Oh,
here.
it's
Oh,
here.
this one.
Like near. Yeah.
Yeah, this one. Correct. Okay, so it's in the elasticity and vibrations part. So this is related to springs.
Mm-hmm.
All right. This is more, I think, just related to light and sound kind of problems. Okay, so this is the formula, the square root of k over m, and we're just going to use that for the, and we know the value of k was 90, and mass was 10, I think, yep. All SI units, so you don't really have to worry about the sign. The answer will just be 3. What will be the units of it?
Radians per second.
Okay. The reason for the units being radians per second is because it's angular speed, right? So it's this is the angle, and then per second is always whatever you use for speed, so radians per second. Okay, so your final equation is just going to look something like 60. The A was 2.5, and then you have cos. Omega is 3 radians per second times t, and the phi is just 0, so you can just put 0, you don't have to write it at all. That'll be your final equation.
Got it.
Okay, so that's A. B is what is the total mechanical energy? When they say total mechanical energy, it's kind of like Bernoulli's equation. You have to combine the kinetic energy and the potential energy. There's no pressure and stuff here because that's for liquids. But mechanical energy, when they say, or total energy, when they say, you have to combine all the energies. In this case, just kinetic and potential. You should have the formulas for kinetic and potential energies. Kinetic is just half mv squared. Potential energy is just half kx squared. Okay, and I think you have the values of, oh no, we don't have the velocity. And it kind of depends where exactly you're calculating it, because you could calculate it along any part of this journey. You could do it here, 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 anywhere. Because, according to law of conservation of energy, energy is always conserved. Same like Bernoulli's principle, right? So you could do it anywhere. I would choose to do it here because I know the most amount of information about this point, correct?
Yeah.
Like I know the x value here, I know the t, and I know that because I'm holding it, it's resting. And so the speed is going to be 0. Like I know a lot of information about that point. So this this was the equilibrium position, and I stretched at 0.25 meters. That's this is the delta x. Actually, the formula is usually delta x squared. But in any case, your delta x is going to be this. I choose this position to do the analysis. At this position, because you're holding it, right? You haven't released it yet at t equals 0. Velocity is just going to be 0, right?
Yes.
So because velocity is 0, this whole term becomes 0. And you'll be left with half. And then k, is just 90 meters per second. And you know that delta x at this position is 0.25 because that's how much I've stretched it. And if you do the calculations, you'll probably get an answer, and that will be your total mechanical energy. It should be in joules. You don't have, all the units are SI, so you can write it as joules or you can write it as Newton meters. They're both correct. Okay, that was not bad. That was easy. Now let's do part C. At what time does the mass first arrive at x equals 0? At what time would the mass arrive at x equals 0? This will be answered by the equation we just made over here. This equation. They're saying find t when x is 0, right? That's essentially what they're saying. So anytime you see a question where they give you the position and ask for time, or they give you the time and ask the position, you will be using the equation that you made, the equation of the position graph. So here we will simply just use the equation. Using the equation. I'm not going to rewrite it. I'm just going to plug in the number. So x is
Mhm.
0, and we're looking for t, right? So
Yeah.
this is more like a trigonometric equation at this point.
Mhm.
First, divide by 0.25 on both sides. Cancels here. 0 over this
Mhm.
is just 0. Cos 3t. To find 3t, so it's more like saying cos 3t is equal to 0, right?
Yeah.
And so then 3t would be cos inverse of 0. You can do
Mhm.
this in your calculator, or we can
Mhm.
look at the graph of cos.
Yeah.
This is the cos graph, right? This is 360, 180, 90, 0. So it's kind of like saying, when does cos become 0?
Mhm.
It'll do so at 90, or pi over 2. Like if you're, so this is pi, 2 pi, pi over 2, right? So
Mhm.
your calculator will say 90 if it is in degrees mode. If it is in radians mode, it will give you like a decimal number,
Uh-huh.
which basically just means like 90 degrees or pi over 2. Okay.
Mhm.
And then you can find your t by just dividing by 3 on both sides. So pi
Yeah.
over 2 divided by 3, that's just pi over 6 seconds. So at pi over 6 seconds, um, you can convert that to decimals if you would like. That'll give you a more appropriate answer. That's when x will go to 0.
Okay, could you just explain in brief, like the
Mm.
like for like the graph, the pi, like the values, how are they like that? Because like I had
Oh,
an idea,
yeah.
but I don't remember anymore.
Oh, yeah, yeah, yeah. Okay, okay, yeah. So both sine and cos graphs, actually, let me just do them both together. They both complete one cycle in
Mm.
in 360 degrees. It's like a circle,
Yeah.
right? From 0, and then you go 90, 180, 270, 360, right? Oh, 180, 270, 360 back. It's like a circle.
Yeah.
So for a sine graph, this is going to be for a sine graph. You start here. This is one cycle.
Yeah.
We know one cycle is 360 degrees.
Mhm.
In radians, that's 2 pi. You know that,
Oh,
right?
yeah.
Okay. Right halfway is 180 degrees, which is pi,
Yeah.
right? And halfway of that is 90 degrees, which is pi over 2.
Okay.
And then between 180 and 360, the half point there is 270 degrees, which is 3 pi over 2.
Mhm.
Okay. For sine graph, um, the max is 1, which is reached at 90 degrees. Then you have 0, which is reached at 0, pi, and 2 pi. All three of them will give you 0. And then the lowest point is -1, which is reached at 270 or 3 pi over 2 degrees. Replicating or trying to replicate the same thing for a cosine graph, actually. Maybe I'll just extend it. If I do that, cosine graph starts at the max position, but the cycle is still like this, right? It's one complete
Mhm.
cycle. Again,
Yeah.
360 degrees or 2 pi is the total. Starts at 0, obviously. Right, the midpoint is 180 degrees. Midpoint between 0 and 180 is 90. Same 270, so this is pi. This is pi over 2. And then 270 is 3 pi over 2. So for
Yeah.
cos, you reach your maximum 1 at position 0 and at
Mhm.
position 2 pi.
Yeah.
You reach 0 at two positions 90 and 270. They, in the question, they only asked you when it first arrives. So you only had to think about this position. If they asked you like do consequent, then the graph just keeps like it's like a spring. It will keep
Yeah.
coming to the 0 position again and again. You can find it as many times as you would like, but they
Mhm.
just ask for the first.
Good.
And then the lowest point here is a -1, which you will get at 180 degrees. Okay, so this is where I got the pi over 2 from, like
Yeah.
here. Okay, all good?
Yep.
Okay, good. Any other questions before we proceed?
Yeah, I'm done. Next one.
Okay. Part D is speed of the mass at x equals 0. So when x equals 0, what is the speed? And then what is the speed when x is 1.5? So we have um, to find the speed when mass at when x is at 0 position, which is the equilibrium position.
Mm.
X equals 0, oops, is the equilibrium position. That's over here. What do we know about the equilibrium position? So it's after you've released it. So you had this mass, you kind of
Mm.
released it, and then it passes through this position. When it passes through this particular position, obviously it has some velocity, right? And that's what we're calculating. So it does carry some velocity with it. Um, do you think there will be any potential energy at the equilibrium position? Like by potential energy, I mean any stretch or compression. That's what causes potential energy. At your
Mm.
equilibrium position, would the spring experience any stretch or compression?
No.
No, exactly. It wouldn't because it's the equilibrium position, right?
Mm.
Um, so at x equals 0, spring experiences maximum velocity. It's just a fact, which means there will be some velocity. You don't need to know what it is. We'll
Mm.
calculate that. But also, spring does not experience any stretch or compression, meaning potential energy is going to be 0 because delta x is 0, right? There's no stretch or
Mhm.
compression.
Yeah.
Okay, so again, total energy is your kinetic energy plus the potential energy, right? Oops, kinetic and potential. And we just established that potential is going to be 0 because delta x is 0. Remember, potential
Mm.
energy is half k delta x squared.
Yeah.
So if delta x is 0, the entire thing is 0, which means all of the energy is equal to Ek. Now,
Mhm.
do we know the total energy?
Mm.
We actually just calculated in this part,
Yeah.
right? Remember
Yeah.
I said you are going to have all these little red dotted regions and every single one of them will have the exact same total energy because the law of conservation of energy, right?
Yeah.
So we're going to use the using total energy from part B. So you'll use that and you'll put that equal to half mv squared. You know the mass of the spring, and
Mm.
from there you can just easily calculate velocity, which will just be 2 times the total energy over m square root of that. I just rearranged it
Yeah.
like, let's say this is E total. So first you
Mhm.
move the 2 to the other side, then you have oops, and then you have mv squared, and you divide by m on both sides, so this
Mhm.
cancels, and then you take a square root because you know it's v.
Mm.
So that'll be the square root of that over m. Okay,
Yes.
good. Oh, we also have to calculate it at x equals 1.5 meters.
Yeah. 0.15.
Oh yeah, 0.15. So that is actually an interesting position because it's just, you know, probably somewhere here. It's not the max position. It's not when x equals 0. Max position was 0.25, right?
Yeah.
Oops, 0.25. So it's somewhere in the middle. So there's
Mm.
some extension, 0.15 meters, which means it's going to have some potential energy in it. And because it has now left, it will also be moving with some velocity. So it's going to have both the components. So for that, we'll just do the potential and kinetic together. Total energy, again, you can use the exact same from part B.
Yeah.
Part B's answer. They probably gave the answer. Oh, here, 2.8125.
Yeah.
So 2.8125 joules. And that will be equal to your velocity squared, and this is half k delta x squared. We know delta x is 0.15, right?
Yeah.
You know k, you know this, you know that, you know that. You know everything, and you can just rearrange for v.
Got it.
Okay, so
Yeah.
yeah, just rearrange for v, and then we'll rearrange for v. That's the only unknown, and you have everything else.
Yeah. So delta x is gonna be 0.15.
Correct. Yes. Okay,
Yeah.
good. Perfect. And then it says sketch the graph of xt. It's gonna look something like this because it's a cos graph. So when you sketch the graph, you just have to use this equation. This is going to be your maximum point. So you know how here it's 1, the max point? In your graph, your max point will be 0.25.
Yeah.
So I'm going to just copy paste this equation because our graph is going to be based on this.
Okay.
Oh, I'd rather just write it. Okay, graphing. So the equation looks something like this. 0.25 cos 3t. Just for reference, this is what your cos graph is going to look like. You need to figure out the max and the min point. You need to figure out this period, because this is just for y equals cos x. Remember, there's no anything with x. There's no like amplitude for this one. When you have these values, the graph will slightly change because this affects your max, amplitude affects your max value, and this affects your period. You know how it's usually just 2 pi because the cos graph is 360 degrees long, like the period is 360 or 2 pi. That's when this value is just x. So when you have this, it's going to affect your period. So the max value, which means the a value is 0.25, that's fine. How does this affect period? So your period is going to be 2 pi divided by whatever this number is, omega. So it's going to be 2 pi over 3. That's going to be your new period. Okay. So when you construct your graph, just make a cos cycle. And then just say this is going to be 0.25. So if that is 0.25, then this is going to be negative 0.25, right?
Yeah.
And the period, instead of 2 pi, this is 2 pi over 3. Yes?
Yeah.
Good. And then you can put xt here, you can put t here. What is the half of 2 pi over 3? So 2 pi over 3's half. That would
Pi
be
by 3.
pi over 3. Yes, because you will do it this way. So the 2's will cancel, right? Okay. So that'll be pi over 3. And then the midpoint of 0 and pi over 3 is pi over 6. And you can find the midpoint of pi over 3 and 2 pi over 3. That'll be 1.5 pi over 3, which is, you can convert it into Something like that. I think 3 pi over 6, which is pi over 2. You can use your calculator, literally just like add 1 over 3 and
Mm,
add 2 over 3 and just divide that by 2. You'll get
mm,
1 over 2. So that's why pi over 2.
mm,
And that's it. That's the graph.
mm.
Okay, does everything make sense?
Yeah, so T is equal to, what's the answer for that? Mm,
T? T has no answer. Were we supposed to find T? No, it's just sketching the graph. What do you mean by T? T is
like sketch
the,
a graph of x of T.
yeah, it just, what that means is your output is the position function, and this is it's literally, you know how y equals something?
Yeah,
That literally is the y-axis is here and x is here. That's what they mean
yeah.
by that. Like the graph
Okay.
of x at t means the output is x at t, which is your position function.
Mm-hmm.
And then you just draw it based on this equation on the horizontal axis.
Okay.
Okay. All right. So that's,
According to the problem, they've given it like T is equal to 2 by 3 pi seconds.
yeah, which is the period, this one.
Okay.
That's like
Yeah.
the end of the cycle. So are you asking how we got this?
No, I mean like that's what they like for the value of T, that's what they wrote at like the bottom of the graph, like T is equal to 2 by 3 pi seconds. So I assume that's the one.
Oh, they probably just, that's the, you don't have to write that. It's 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 just saying that the period of the graph is 2 pi over 3, which is kind of what we just said over here. They
Yeah.
just wrote that in words, maybe.
Yeah. Okay.
Okay, good. Um, okay,
Mm.
that's the third question. We only did three, there are four more to go. Wow,
Yeah.
that's a okay, let's do this. Maybe we'll do until 9:30 today, and
Okay.
then um I can see and try to find a time on Monday, maybe, to do the rest. I don't know.
Monday.
Do you have an
Is it
exam?
possible? Yeah, like is it possible that like if you can extend the time today, is it possible?
Um, I uh I still have to eat dinner and I'm really hungry.
Oh, okay.
That was the only reason. But huh. Let me just see the type of questions. We have one which is related to electricity. Okay. That these are actually not too bad. They're just use a formula. Okay, then we have this. This is balancing of forces, but electric, and then you have a ray diagram. Hmm.
Will
It,
tomorrow be possible, like in the morning or, just,
so tomorrow I have
yeah.
back-to-back classes like 8 a.m. to 12
Mm,
p.m. and then I'm going for a wedding at 1, so I've got 1 hour to get ready. And then
mm.
um so I'll be at the wedding the rest of the day. What time is your exam on Monday? Like what's your schedule like?
I have an exam like at 4 p.m.
Oh, so you'll be studying
Mm.
for that the whole day.
Yeah.
Yeah. And when is physics Tuesday?
It's on Tuesday, yeah.
Oh, okay. Monday.
Mm.
Yeah, Monday's pretty like okay.
Like,
Hmm.
um,
We okay, let me see how I'll try to
the
see
thing is,
how
the
much
thing
we
is
can.
that the exam that I have is like an
Yeah.
online exam. So just
Okay.
because like I have another exam after physics, I thought that I would
Yes.
finish it tomorrow. So and then I would like go for my exam on Tuesday. But there's like a time, like there's like a period that I have on like Tuesday that I can like I have time for the exam like the day after as well. Like it's like
Oh,
yeah, so that I can like if like okay on Monday if any other time is possible, I could do that.
okay. I see. Hmm. Okay,
What
let's
timing
think.
is what times are possible for you on Monday?
So I'm booked 3 p.m. to 8 p.m.
Okay.
I will, we can do
Okay, could we do it Monday
8:30 p.m.
morning?
Yeah, Monday morning could work. I don't think I have to go to work. We could do Monday morning. Yeah, what time works?
Okay, how about like 11 to 12?
Yeah, that works.
Okay, yeah.
I'm gonna just block my schedule from 11 to 12 before.
Okay.
Um, okay, and let's try to do, maybe we'll try to do one of the electricity questions because I think that'll be, or even this is gonna be easy. We can do one of these
Okay.
and then we'll do the rest later. It's gonna be very similar to what we just did.
Yeah.
Anything that's related to waves, it's going to be very formula based. So,
Mm,
and now probably you can read this equation. Like this is the amplitude, right? A value,
mm,
just the maximum. And this
mm,
is kind of like your, um, it kind of tells you about your period, but this is like omega, which is like your angular velocity, right? This is amplitude. And this is going to be that phi, which is like how much phi means like how much you move to the left or to the right. Like it's literally this phase shift left, right.
mm,
Okay, that's what phi means. Um, okay, so first one is determine wavelength, frequency, and speed of the sound. So frequency is, you'll have formulas for all wavelength, frequency, and then speed. So we're going to
mm,
go to this formula sheet, go to the waves section, and look for, okay, there we go. This is going to determine your wavelength. Wavelength is going to be related to k and 2 pi. By the way, what is k is basically this value over here. Oh, I'm wrong. I thought there's no x associated with it. Sorry. This is not phi. There's an x here. I didn't see that, which means this is k value. If there was something just written by itself, like 3.1, and that's it,
mm.
alone by itself, that's what phi is. So, sorry, my bad. This is actually k, whatever's written with x. So, for wavelengths, you know k is equal to 2 pi over wavelength. So if you
Mhm.
rearrange, wavelength is just 2 pi over k. So all you
Yeah.
have to do is just divide 2 pi with this number, k.
Okay. Yeah.
And use this equation, use your formula sheet because it's literally telling you everything, right? Like this is your
Yeah.
angular velocity, this is
Yeah.
k. The last thing we want to do is find speed.
Mhm.
Do we have a formula that connects speed to anything? Not over here, I think. Well, there's this one, but this is c is the speed of light.
Mhm.
Let me see if there's any other speed formula. You can technically you can use this because c for you will just be v because c specifically means speed of light, but you
Mhm.
could use that. That's one way. The other way, mm,
Mm,
you could play around with your units actually too, if you really think about this, because this is radians per second, this is
mhm.
radians per meter.
Yeah.
Speed is meters per second.
Yes.
So if you just divide your radians per second, right? If you divide
Mm,
radians per second with the K, which is radians per meter, you can
yeah.
get your answer in meters per second. Like
Mhm.
that's a
Yeah.
unit play on the stuff that's given to you, but you can
Yeah.
also use V is equal to lambda F because you will have your frequency and
Yeah.
wavelength already, right?
Mm, yeah.
So for part A, you can do your wavelength using this formula. You have all the numbers.
Mm,
Frequencies, by the way, just 2 pi, omega is 2 pi f. This is
yeah.
angular speed.
Mhm.
Frequency is just um, per seconds. Oops, not k, f. So if you rearrange, f is just omega over 2 pi, so you can use that. And finally, for speed, you could either use just multiply the f and um, these two answers, f and lambda,
Mm-hmm.
or you can use omega over k. They both should work.
Mm-hmm.
Okay, next up, we're doing sketch a graph of epsilon x0 and epsilon 0 t. Okay, so basically x0, okay, the graph that we're given, I always have a hard time using this epsilon symbol, but okay. The graph that we're given is an xt graph, right? And
Mm-hmm.
because it has variable t and x both in it. So
Yeah.
it's kind of like 250. Sorry, I'm not going to add units just because let's just get over with it. And then t minus 9.597x.
Mm-hmm.
When they say sketch the graph of x0, it means put t as 0. So if you put t as 0, this whole term disappears, right? So
Yeah.
you'll have just negative 9 point this, right?
Mm-hmm.
And so um, it's going to be a sine function. We know that. Um, we're not used to, oops, we're not used to seeing this negative. But
Mm-hmm.
what this negative would essentially mean is there is a reflect. So this is the real graph. This negative means there's going to be a reflection in the y-axis. So it's kind of like your graph's gonna kind of look like this. There's a better way to do this. You know, I said the cos graphs are even graphs. So if this was a cos function, by the way, if this was like a cos with a negative whatever,
Yeah.
you know that cos is an even graph. So even if you put like a negative theta, it's just the same thing as cos theta. So you could completely just ignore the negative
Mm-hmm.
if this was cos. But a sine function is actually an odd function, which means if you have sine negative theta, it means the sign still persists, but we can take it outside.
Yeah.
Okay. So what you can do is just to make it simpler, you can just move the negative outside because sine is an odd function.
Mm-hmm.
And then all you have to do, again, this negative means you're gonna, instead of doing it this way, you're gonna get, your graph is gonna be reflected like this. That's all this means. The
Mm-hmm.
maximum is still 250 and negative 250 because that's determined by the a value, right?
Well, yeah.
Your period, remember, period is determined by this value. So period is 2 pi um, over this value of 9.2597.
Mm-hmm.
That's going to be 2 pi over 9.597. Let me just do the math real quick. See if we get the same answer. So 2 pi, you could literally do it on your calculator and then just divide by 9.597, and I get 0.6547.
Mm-hmm.
Okay, so this value over here is going to be 0.6547, and then you can do the half of that, half of that, half of these two, and then that's basically just that's your graph.
Okay.
Okay, and the
Mm-hmm.
same thing if they want you to do the graph of this, just put your
Mm-hmm.
x as 0, right?
Okay.
Instead of putting t0 and the t term disappears, you just put x
Mm-hmm.
as 0 and this term disappears, and the exact same thing you will just do it here. Wait, it's 25. I've been writing 250. Sorry about that.
Oh, yeah. I didn't realize it.
Yeah,
Mm. Yes.
it's 25. Okay,
Mm.
so the other graph will be the exact same. Other graph will be the exact same idea. Okay.
Mm. Okay.
All right. So that's that. And then the last thing is Suppose this harmonic sound wave enters through the open end of the tube that is closed on the other end. Okay. And then it says, if the length of the tube is this, sketch the standing wave that forms in the tube. So you can have different types of tubes. Some are open-ended, some are closed-ended, and some is like this one is like semi-open, like one end is open,
Yeah.
one end is closed, which
Uh-huh.
means you're gonna have to go and see. I don't know if they have different
Mm,
equations for different.
they might, I think. It's like,
Okay, we need um I don't I think we may be able to use like it's actually these,
mm,
but they didn't say which one is what. So if you have um if you have a closed tube versus open tube, these are the two different formulas that you can use. I'm just gonna double check which one is for what. This
okay.
one of them is for open, one of them is for closed. So let me just quickly
Um, yes, I think
open
that one's for open. Like the 4L one's for like the semi-open tube. I
the
think the
four one is the
same.
semi-open.
Yeah.
The open-ended to, oh yeah, this one is open, and then so this one should be the one end closed, one end closed. So the semi-open, right? Hold on, let me just do. Uh, okay, I'm gonna just copy paste this image that I just found. I think it'll be really helpful. Oh, I'm not using my, never mind. I will show you it here. Oh, there we go. So apparently this is the formula,
Mhm.
which is tube for tube that is closed at one end. Um, we will be, it's like first harmonic and then the second and third and so forth, so on and so forth. It
Mhm.
basically means, um, so third harmonic, you have one node, two antinodes, and then you have two of these, so on and so forth. But essentially what it's trying to say is that it's the 1/4 formula.
Yeah.
So let's do this. So F, which is frequency, is NC/4L.
Mhm.
Okay. Frequency is NC/4L. What were we finding? We're finding the length of the tube.
Mm.
Um, do we have frequency? Yeah, we have frequency from here. Um, speed you will have from here.
Mhm.
So you can use that, or you can use lambda because you know that speed is frequency times lambda, right? So
Yeah.
if you replace the c with f f lambda
Okay.
over 4L,
Yeah.
um, then f and f cancels. So your n, if you rearrange for n, it will just be 4L over lambda.
Yeah.
Because the goal is to find n, right? Like you could do that 4L over lambda, or you could just use the frequency and speed, like that's fine as well. So n is
Mhm.
just going to be 4 times the length. Do we have the length? Oh yeah,
Yes.
1.14.
1.1457.
Correct. And then you divide it by whatever wavelength you got from part A,
Yeah.
and that'll be your
Got it.
answer.
Mm.
Depending on n, let me see if I can copy paste this because this image will be useful to help you
Yeah.
draw. Copy and allow. Oh, great.
Yeah.
Okay, perfect. This will be the drawing when n is equal to 1. This is the drawing when n. Hold up, actually, 1, 2, 3, 4. This is when n equals 5. Oops, I can't draw. Why? Pairs. Oh, there we go. Okay. So this is the formula when n equals 3 and n
Yeah.
equals 5. The number of nodes is always 2 less, right? And here when n
Yeah.
equals 1, there are no nodes.
Mm.
Um, let me just look at the answer just to see.
I think the end that they got was 7. So if it's 7, how is it gonna
Okay.
be like?
So for n equals 7, you should have 4 nodes, right? Because you're
Yeah. Yeah. Yeah.
right for n equals 7, you're going to have 4 nodes.
Mm.
So what you can do is just make 1, 2, 3, 4. Oops, it's not very accurate, but essentially you're going to have
Mhm.
like 4 nodes and just leave one of the ends open. That's all.
Okay. Got it. Yeah.
Okay, so
Yeah.
I think we will. Okay, we have 20 minutes. I'll just go until 10, so we'll do 2 hours, and
Okay.
then if anything, we can do Monday. Okay?
Okay. All right.
Okay, let's do this. This is charges. So you have two stationary charges. One is located at 2.50. So it's probably this one because this seems to be 0. So this is like at the distance of 2.5 centimeters.
Mhm.
And the other one is at a distance of negative 2.5 centimeters, right? This one. Both these charges. Consider P is located at the origin. So this is 0, 0, makes sense. 1 microcoulombs is 10 to the power of negative 6 coulombs. That's okay. Calculate the electric potential P. Okay. We have to look for what you can do is just look for the formula for electric potential
Yeah.
in your formula sheet, which is right here. Um, electric potential. It's V. So E over Q, that's one of the formulas. Is it somewhere here? Nope. These are charge flows.
Hmm.
You should be able to, or you can rearrange, like if you know that V is E over Q test, right? And you
Yeah.
know V is basically this,
Yes.
which
So
is
it's
K Q1
Q1.
Q2 over R, oops, over R. And then you put this Q here. One of the Q's will cancel, so it'll just be K Q over R, where Q will be the charge that you're calculating the
Mm.
electric potential for, right?
Yeah.
So sometimes you may not be given the formula directly, but you can
Mm.
derive it from the given formulas, okay?
Mm.
So we're going to use the electric potential formula, but there are two different charges. So we
Mm.
need to combine both of them.
Yeah.
So electric potential, the formula was KQ over R. That's the generic formula, but we have two charges, so
Mm-hmm.
um,
So it's gonna
we
be
can do,
KQ1 by
yeah,
R1. Yeah.
yeah, exactly. And then you just do the math, and that should, you have the K value. K value is,
Mm.
it's a constant, um,
Mm.
9 times 10 to the 9 coulombs.
Mm. Yeah.
And then you're given Q1's charge, right? But make sure that you convert it into SI units, which is coulomb. Otherwise, your answer will be in different units. So I'm going to make sure that's consistent. And that's it. That's for P. B is electric field. Electric field is what we just saw, which was K Q1 Q2 over R, right?
Yeah.
That's where we got the potential formula from. So again, calculate the electric field magnitude and direction. So here the magnitude is easy, just plug in the numbers. For the direction, you just have to look at the sign, like if it's going this way, positive or negative or whatever that is. So you have to look at the signs of the answer and then determine which direction it would be. So for the electric potential, oops, notice that electric potential is a vector. Sorry, electric field is a vector, and electric potential isn't. It's just a scalar. So you can just use this formula K and then actually there is no charge at the position P. So when you're calculating electric potential due to the first charge, there is no second charge. So you can just basically use Q1 over, actually hold up. I think I did it. No, I think there's one Q and two R's. It's R squared and E. Hold up, this formula is wrong. Electric field, electric field, electric field. Electric field is force over Q. That's actually this one. This E is the electric field, which is force over Q. So force is K Q1 Q2 over R squared. That's force from here. And electric field is going to be, I think this is electric potential and this is electric energy, not electric field. So electric field is force over Q. So when you do that, that'll be K Q over R squared.
Okay, yeah, so it's gonna be
KQ over R squared. KQ over R squared. So you're going to do that for the first charge over R1 squared. And then you're going to do that for the second charge, Q2 over R2 squared. And you do that, and that's going to be your total energy. The other thing is, because you're calculating from point P, this is negative, this is positive. For positive charges, when you draw the electric field lines, you have to consider where the electric field lines are going in or out of charges. So for example, when you have a negative charge, the electric field lines all enter into the charge. It's like this. When it's a positive charge, electric field lines always go out of the charge like that. So if we do it over here, towards point P, this is going to go this way because positive charges always radiate electric field lines outwards. But we don't really care about these charges. We care about, at point P because that's what we're being asked. For negative charges, the electric field lines are always going into them. Kind of like this, right? So from the point of view of P, like from P, the line is going to go this way. So for both of them, the direction is going to be positive. So you're going to add this in the positive x direction, this one as well in the positive x direction. So whatever you get at like the result of this, it should be in the positive x direction.
Yeah.
Okay, and
Mm-hmm.
but the concept for that is to know how electric field lines behave for positive or negative charges. Okay, so it's just plugging in the values like
Mm-hmm.
part A, so I'm just gonna let you do that.
Okay.
And then this one is consider we now place a test charge at position P. So initially we had a charge here, we had a charge here, but there was nothing. So now we're putting like a test charge, which is positive, no, negative 2 microcoulombs charge at position P. And we're been asked to calculate electric potential energy, right?
Yeah.
Electric potential energy is K Q1 Q2 over R. This is what we derived this formula from.
Yeah.
This is from the formula sheet, right?
Mm-hmm.
So all we got to do over here is you can use that for both, or because we derived this formula for potential, we know it's just, what is it actually? Q times
Oh,
the
V.
potential, right?
Yeah.
Yeah, Q times V. And this Q is going to be the charge that we're testing it for, right? It's, if you look at the formula sheet, it's the Q test
Yeah.
charge. I hope. Does it say here? Yeah, it says Q test times V, right?
Yeah.
So there are two ways to calculate it. You could do it
Mm-hmm.
this way with the formula, or you
Yeah.
can do Q test times the V that you
Mm.
found
Yeah.
in part A.
Okay.
Okay.
Yeah.
The next electric force. Again, electric force is two formulas. Oops, sorry, this is C and so D. Force is just, K Q1 Q2 over R squared. So you could do that because you do have the values. Or we just realized that force was Q times the electric field, right?
Yeah. Yeah.
So we just calculated electric field over here, so why don't we just use that and make our calculation easy?
Yeah.
And this is going to be the test charge, so the negative whatever charge you had.
Mm-hmm.
Because this Q test is negative, your answer for force is going to be negative as well.
Yeah.
And then it just depends. You just make sure you just put the signs and see whatever is the end result when you just do the calculations at the end, right? So extremely formula based. The only concept that you had to use here was the concept of the direction of electric field lines.
Mm-hmm.
Are we good with
Yeah.
everything here?
Yep. Yeah. Yeah.
Good. Um, the next thing is
Okay, sorry,
B6.
for the force, is it which direction is it gonna be in?
Depends on the sign. So if it's going to be, so if it's, uh, let's just do the calculation then. So it's the negative coulomb, negative 2, and electric field. Do they give the answer? Yes, 7.2
Mm.
times 10 to the 7 newtons per coulomb, which means you're going to get a negative 144 Newton force, which means it is going to be in the negative direction,
Yeah, okay, that makes sense.
negative x direction. Okay,
Yeah.
all right. Moving on to this question. Um, this figure shows a proton. So we have a proton over here. We have its mass, we have its charge, whatever we need. It's at rest in water.
Mm.
Extremely important term. Because when
Yeah.
something, remember the very first question, when something is stationary, when something is at rest, it
Mm.
means the sum of all the forces acting on it is zero.
Yeah.
Okay. The water has a dielectric constant of 78.5. There are
Mm-hmm.
these two parallel plates. Each plate is a square with a side length of this,
Mm-hmm.
100 meters, oriented horizontally one above the other. So kind of like one over the other, and then there's this charge right here.
Yeah.
Um, and of course there's water in here. It's filled with water. Okay, by setting the potential difference across the plates to delta V, induced charge on plates generates an upward electric force. Okay, so this proton is experiencing an upward electric force. Um, in this case, the upward electric force and downward gravitational force exactly cancel. Even if they didn't write it, you would know that because it's at rest, so they must cancel, right?
Okay.
Um, it says calculate the Q required to make this happen. This is the Q. So we basically need to find a charge
Okay. Is
that
it
is going.
fine? Is it fine if we do these two questions like on Monday then?
Yeah, actually, that would,
Yeah.
yeah, let's do
Okay.
that.
Okay.
Yeah, it must be a lot. But yeah, these two would be good for Monday.
Okay. All right. And the 11 a.m. it's actually my time, so that's like the PEI time. So
Oh, right.
yeah.
Yes. Hold on, let me just stop the recording. Um, okay. Yeah, that's